Hi, welcome to the final section of the course titled Coding Best Practice and Testing the Functional Code. In this section, we will start with coding best practices in functional C#, then look at separating the code from domain logic and mutable shell, and finally see running domain logic in unit testing and adding the mutable shell into code. So let's begin with the first video titled Coding Best Practices in Functional C#. In this video, you'll first see SumUp function, then refactor the UpdateUser method and make it mutable, and finally learn CreateMember method, SaveMember method, and CreateAddress method in detail. The functional approach has the concept of a pure function. This means that the function will produce the same result as long as we pass the exact same input. Now let's start with our discussion to create the better functional code by following the coding best practices. We will start with preventing dishonest signatures. As we saw in an earlier section that we use the mathematical approach to construct our code in functional programming. In other words, functional programming is programming with mathematical functions. There are two requirements that mathematical functions must fit. They are, a mathematical function should always return the same result whenever we supply the same arguments. The signature of the mathematical function should deliver all the information for the possible accept input values and the possible produced output. Let's take a look at the code, which we can find in the honestsignature.cs project. Now we will see this highlighted code snippet. By examining SumUp function, we can see that we will retrieve the same output every time we pass the same inputs. Now let's examine generateRandom function. In this highlighted code, we can see that we retrieve different outputs although we pass the same input continually. Now we have run generateRandom function. From this code snippet, we invoke generateRandom function 10 times by passing the exact same argument, that is 100. Now let's run generateRandom function. As you can see, the function returns a different output for each of the 10 invocations. So, we have to avoid functions such as generateRandom function in order to create a pure function since it is not a mathematical function. Now let's take a look at the following divide function, which will divide the first argument by the second argument. The divide function looks similar to the SumUp function since the signature of the divide function accepts any two integers and returns another integer. So if we pass the exact same argument, it will return the same output. However, how about if we pass 1 and 0 as input parameters? The divide function will throw a divide by 0 exception error instead of returning an integer value. In this case, we can conclude that the signature of the function does not deliver enough information about the result of the operation. It looks like the function can handle any two parameters of the integer type, but it actually cannot. To solve this problem, we can refactor the divide function to this highlighted code. In this divided function, we add the nullable type by adding a question mark after int so that the return of the function can be null. We also add an if statement to make sure that the divide by 0 exception error will never be thrown. Now we will see refactoring a mutable class into an immutable one. Immutability is very important to functional programming since a mutable operation will make our code dishonest. As we saw previously, we need to prevent dishonest operations in order to create our pure function approach. Immutability is applied to a data structure. For instance, a class means that the objects of this class cannot be changed during their lifetime. In other words, we can say that a class is mutable if the instances of the class can be changed in some way, while it is immutable if we cannot modify the instance of the class once we create it. Now let's take a look at this highlighted code, which can be found in the Immutability.cs project to continue our discussion. As you can see in this code, we have a simple composition. The user membership class consists of _user and _member since properties. We can also see that user class is immutable since all the properties are defined as read-only. Because of immutability, the only way for the UpdateUser method to update the _user field is to create a new user instance and replace the old one with it. Note that user class itself doesn't contain the state here, whereas the user membership class does. We can say that the UpdateUser method leaves a side effect by changing the object's state. Now let's refactor the UpdateUser method and make it immutable. So here I've refactored the UpdateUser method. As you can see, the UpdateUser method no longer updates the structure of the user membership class. Instead, it creates a new user membership instance and returns it as a result of the operation. By refactoring the UpdateUser method, we have eliminated the side effect from the method. Now it's clear what the actual output of the operation is. The usage of immutable data makes the code more readable, and also helps to provide a good understanding of what is going on right away without too much effort. Now we will see avoiding mutability and temporal coupling. Sometimes, the use of the methods with side effects will damage readability. The invocation of one method is coupled with the other's method invocation. To make things clear, let's take a look at the code, which we can find in the temporalcoupling.cs project. In this highlighted code, you can see that we have a membership data class, which processes a new member. It retrieves input parameters named member name and address string and uses them to insert a new member in the database. The process method in the membership data class invokes the CreateAddress method first, which will create the address and then save it to the private field. The CreateMember method then retrieves the address and uses it to instate a new member parameter, which is saved in another private field named member. The last method, the SaveMember method, saves the member to the database. There is a problem here. The invocations in the process method are coupled with temporal coupling. We have to always invoke these three methods in the right order for this code to work properly. If we don't place the method in the right order, for instance, if we put the CreateAddress method invocation after the CreateMember method invocation, the resulting member instance will be invalid, since the member will not retrieve the required dependency's address. Likewise, if we put the SaveMember method invocation above others, it will throw null reference exceptions because, when it tries to save a member, the member instance would still be null. Temporal coupling is a consequence of the method's signature dishonesty. The CreateAddress method has an output creating an address instance, but this output is hidden under a side effect because we mutate the address field in the membership data class. The CreateMember method hides the result of the operation as well. It saves the member to the private field, but it also hides some of its input. From the signature of the CreateMember function, we might think that it needs only the name parameter in order to create member, where it actually refers to a global state, the address field. This happens to the SaveMember method as well. To remove the temporal coupling, we have to specify all of the input and output in the method's signatures explicitly, or in other words, move all side effects and dependencies to the signature level. Now let's refactor the side effect containing code. This is the refactored code. You can find this in temporalcoupling.cs project. Here we have refactored the process function, CreateAddress function, CreateMember function, and SaveMember function. Now the CreateAddress method returns address instead of saving it to the private field. In the CreateMember method, we add a new parameter, address, and also change the returning type. For the SaveMember method, instead of referring to the customer private field, we now specify it as a dependency in the method's signature. In the process method, we can now remove the fields, and we have successfully removed the temporal coupling with this change. Now, it's impossible for us to put the CreateAddress invocation method after the CreateMember invocation method because the code will not be compiled. Now this is a side effect code which I have commented it. You can refer to this code if you want. It's available in temporalcoupling.cs project file. Now we will see dealing with the side effects. Although we need to create a pure function in functional programming, we cannot avoid the side effects completely. As you can see in the preceding membership data class, we have the SaveMember method, which will save the member field into the database. This code snippet will explain it clearly. To deal with the side effects, we can use the command query separation (CQS) principle to separate methods that generate side effects and methods that don't. We can call commands for methods that incur side effects in queries for methods that don't. If the method alters a piece of state, it should be the void type method. Otherwise, it should return something using this CQS principle. We can identify the purpose of a method by just looking at its signature. If the method returns a value, it will be a query and it won't mutate anything. If the method returns nothing, it must be a command and will leave some side effects in the system. In membership database class, we now can identify that the process function and SaveMember function methods are commands types and will leave some side effects since they return nothing. In contrast, the CreateAddress and CreateMember methods are queries and won't mutate anything since they return something. Awesome! In this video, we saw coding best practices in functional C#.